There's a lady who's sure all that glitters is gold, and she's buying a stairway to heaven.
Okay, maybe I'm having a little bit too much fun with these videos. It's hard to think that's what rock stars used to look like. God, that's even older than me. Okay, guys. Anyway, hopefully you haven't said, well, Darbo's lost his mind and sent us the wrong video. You're probably just thinking Darbo's just lost his mind. Guys, video on normal distributions. By the way, that was Led Zeppelin, in case you didn't know. I think I explained it in the previous email. My father-in-law's having open heart surgery tomorrow. I'm taping this actually on Monday. So, we've missed so much class so far. I really didn't want to miss, but for obvious reasons, I needed to. So, guys, kick off your shoes, sit back, enjoy. Hopefully, no more music. It's all stats from here on out. But the topic that we're going to look at is normal distributions. First of all, as you know, I graded your exams. They were good. They were fine. They were about where I expected them to be. The first exam is the easiest by far. Now, normal distributions don't get incredibly difficult, but there's going to be some pretty tough, or at least tougher stuff coming up, because I know you guys are up to the challenge, right? So, guys, what's next on the topic is something called normal distributions. What I'm going to do here is I'm going to run through a short PowerPoint that I've prepared, giving you kind of a preview. That I'm going to jump over to what I call docery, where I can actually write and give you some more illustrations. So, guys, anyway, what we have here is a histogram of some vocabulary scores for about 1,000 7th graders. Now, clearly there are more 7th graders than just 1,000, so this would make up a sample of all 7th graders. And I have no idea whether this is randomly sampled or not, but nevertheless it would be a sample. And the vocabulary that we've used so far in the class, since this is constructed from a sample, we would refer to this as being a bell-shaped and symmetric distribution. All right? We know that the appropriate measure of center and spread are the mean and the standard deviation for bell-shaped and symmetric distributions. But keep in mind that this is loosely defined. For example, the histogram that we're looking at currently, which looks like it has to do with some heights of a sample, we would refer to that as bell-shaped and symmetric, when clearly it's not really bell-shaped and it's certainly not symmetric. So guys, again, when we're defining histograms for samples, the terminology bell-shaped and symmetric is loosely defined. Now, do things differ in populations? Well, they absolutely do. And what we do from the terminology associated with samples called bell-shaped and symmetric, we actually use the terminology normal distributions for populations. Now, when we talk about a population, we're talking about the entire group of subjects, elements, dogs, cats, trees, whatever it may be that's under investigation. And we no longer loosely define bell-shaped and symmetric. When we move into a population, a normal distribution is perfectly bell-shaped and it is perfectly symmetric. And there's one drawn there on the screen. Guys, the normal distribution is defined by its center. Again, the bell-shaped and symmetric distribution for sample is defined by its center. And the spread, as you would expect, is defined by the standard deviation. So nowhere in statistics, we've talked about measures of center and spread no longer being separable. There's no place in statistics where this is any truer than in the normal distribution. So the mean defines where the center of the distribution is, and the standard deviation measures the spread around the center of the distribution. Now, guys, we're moving into population, so the notation changes. Where we used to have a mean being x bar, Now a mean for a population is mu. So guys, when we collect a mean from a population, the notation is mu. When we collect a mean from a sample, the notation is x bar. Similarly speaking, I guess, for a standard deviation. The standard deviation for a population is sigma. And while we should know by now that the standard deviation for a sample is s with a small x. Now the notation I've given at the bottom, n, parentheses mu sigma, that's a notation you're going to see a lot when defining a normal distribution. Guys, n, obviously, normal distribution. The number that comes first in the parentheses is the mean. The number that comes second in the parentheses is the standard deviation. Now, there was a study done a few years ago by the Health and Nutrition Examination Study, and what they found is that heights of all adult men were normally distributed. They had a mean of 70 inches, standard deviation 2.8 inches, and again, the heights followed a normal model. So the notation at the very bottom, you would see that we would summarize this by capital N, again, standing for normal distribution. 70 being the mean would go first, and 2.8 being the standard deviation would go second. So that's going to be an important notation that we're going to use throughout the presentation of normal distributions. Now, more in general, given the mean and given the standard deviation, we know more about our distribution, where it's centered, and how much spread we have around the mean. So the pictures I have at the bottom, you can see that in both distributions, the right and the left, you can see that the mean mu is right in the center of the distribution, and sigma defines the first standard deviation above the mean. So it defines the the spread about the mean. So the distribution up to the left has a larger standard deviation, more spread around the mean, than does the distribution to the right, which has less variation around the mean. Well, back to the beginning of the slide, the rock stars. So, guys, what I want to do now is I want to get out of this, and if it'll let me. Okay. And my PowerPoint does not want to quit. So, bear with me here. All right, bring up dosery here, where I can actually do some things. All right, so again, something important is that mu and sigma are for normal distributions. And these define populations. While x bar and sx define bell-shaped and symmetric distributions, or I should say they're the appropriate measure of center and spread for the bell-shaped and symmetric distribution. Let's see if I can get this doing full screen. There we go. That's what I intended to do first of all. So, guys, let's draw one of these and examine some things. You'll get really good at drawing these after a while. But guys, a normal distribution sits completely above the line. It has area of 1 inch squared, or I'm sorry, 1 unit squared. And right in the center of the distribution is the mean. Now guys, if you start at the top of the curve where I'm going right now, and I'll tell you what, I'm going to actually change colors here, and I start to trace down the distribution from about that point, and if I start on the other side and trace the other way, if I draw my distribution correctly between those 2 points, I will have pretty much a straight line. Now it's not perfectly straight, it's just kind of straight, okay? So imagine coming to the center of that line and dropping a line down to our horizontal axis. Well guys, it turns out that, let's see, I need to get this back to white. There we go. That this is 1 standard deviation. Wow. Above the mean. Now, because of the perfect symmetry, if I walk my way over to the other side, finding the same point, drop a line down here, this is 1 standard deviation below the mean. Guys, once I get this distance defined to be 1 standard deviation, I could come on up the same distance and have 2 standard deviations above the mean, 3 standard deviations above the mean, and on the other side I could do the same thing with 2 standard deviations below the mean. Alright gang, let's carefully draw an axis here from, say, 0 to something. And what I want to be able to do here is I want to examine, and that should be far enough, what some distributions will look like. So guys, the first distribution, if we have a mean of say 50 and a standard deviation equal to 10, what's this going to look like? Well guys, we know that we're going to be centered at 50, and 10 units to the right and 10 units to the left is where this straight line, for lack of a better way of putting, a straight line phenomenon is going to occur. So guys, I'm going to be expecting a normal distribution. It's going to look something like that. Contrast that with, for example, a mean of 30 with a standard deviation of 2. Well, the easy part is we know it's going to be centered at 30, but 2 units to the left and 2 units to the right is where that straight line phenomenon is going to occur. So guys, this distribution is going to be very steep and have very little variation around the mean. You can imagine a third one, for example, if we were to have a mean of say 40 and a standard deviation of say 20. So we'd have centered at 40, getting kind of cluttered here, right? Standard deviation being 20 above. So guys, we'd have a distribution that would look something like this. All right, so guys, tapping into this a little bit more, let's show something really important. So if we have a normal distribution in general, Again, smack dab in the center is going to be the mean. This location right here is going to be the mean plus a standard deviation. This will be a mean plus 2 standard deviations. And this will be a mean plus 3 standard deviations. On the other side, we have the mean minus a standard deviation, the mean minus 2 standard deviations, and the mean minus 3 standard deviations. Now gang, there's something called a 68, 95, 99.7% rule. And the 68 part tells us that between 1 standard deviation below the mean and 1 standard deviation above the mean, that we expect 68% approximately of our distribution to fall between those two values. From 2 standard deviations below to 2 standard deviations above, this is where the 95 part comes of this rule. From 3 standard deviations below to 3 standard deviations above, this is where the 99.7% comes. Well, in a distribution defining an entire population, it would make sense that we're going to define the entire 100%. So guys, because of perfect symmetry, if you think about it, 100% minus 99.7% gives us 0.3%. So we would put half of that, 0.15%, in the left tail and 0.15% in the right tail. Now guys, if your decimals and percentages are a little testy, 0.15% is equivalent to about 15 out of every 10,000 subject in our population will have a score that's lower than mu minus 3 standard deviations. And then on the other end of the spectrum, there'll be about 15 out of every 10,000 that'll have scores that are above 3 standard deviations above the mean. Now guys, one of the easiest distributions to deal with that's normally distributed are IQ scores. And it turns out that IQ scores are normally distributed with a mean of 100, standard deviation of 15. Now what that tells us is the following. We can sketch the normal distribution. So in the center of our distribution will be a value of 100. 1 standard deviation above the mean will be 115. 2 standard deviations above the mean will be 130. And 3 standard deviations above the mean will be 145. 1 standard deviation below the mean is 85. 2 below is 70. And 3 below is 55. Using the 68, 95, 99.7% rule, we know that 68% of our data should fall between 85 and 115. So therefore, approximately 68% of people have IQs between 85 and 115. Approximately 95% of people have IQs between 70 and 130. Approximately 99.7%. So in other words, about 997 out of every 1,000 people has IQ between 55 and 145. Guys, not many people, I've heard a lot of people claim this, but not many people has IQ above 145. In fact, how many approximately? About 15 out of every 10,000. So guys, that's going to end this video. The things that I want you to take away from this are rock stars used to look pretty silly years ago. Well, I don't guess they look silly, but they look silly compared to what we look at today. Or maybe they don't. I don't know. It's a good perspective. But seriously, what I want you to take away from this video is when we talk about histograms, if we define a sample, if we're dealing with a sample, the mean and standard deviation are the appropriate measures of center and spread. The notation we use, x bar and sx. And if we get a bell-shaped and symmetric distribution, we call it just that. When we move into populations, the mean and the standard deviation are still the preferred measures of center and spread. But guys, the notation changes when we're in a population. So guys, that's the end of this video. Hope to see you Thursday. There's going to be one more video posted. So take care.